What if the golden age of medicine was over? Imagine a world, not in some distant dystopian future, but right now, where routine procedures we take for granted become a deadly gamble. Imagine chemotherapy, the cornerstone of modern cancer treatment, becoming a death sentence, not from the disease, but from an unstoppable infection that follows. Imagine organ transplants being impossible, a cesarean section being as risky as it was a century ago. This isn't a science fiction plot. This is the terrifying reality of antibiotic resistance, a silent pandemic that is already contributing to nearly 5 million deaths every single year. For decades, we've been locked in an evolutionary arms race with bacteria, and we have been falling desperately behind. The story began with a moment of serendipity in 1928 with Alexander Fleming and a petri dish of mold. Penicillin was a miracle, the first shot in a revolution that saved hundreds of millions of lives. For a time, it felt like we were invincible, but we grew complacent. We overused and misused these precious drugs, giving our ancient bacterial adversaries countless opportunities to learn, adapt, and fight back. They share survival blueprints, resistance genes, amongst each other like a planetary-wide superintelligence, constantly upgrading their defenses. Our pipeline for new antibiotics has run dry. But what if the next great weapon in this war wasn't discovered in a remote jungle or a deep-sea trench, but was instead imagined, designed, and built, atom by a powerful artificial intelligence? Today, we are pulling back the curtain on a revolutionary breakthrough from the brilliant minds at MIT that could fundamentally change our fight against the world's deadliest superbugs. We will uncover how scientists have unleashed a generative AI to invent millions of entirely new antibiotic molecules that have never before existed on Earth. We'll meet the first two of these AI-designed assassins, a pair of compounds with the power to defeat two of the most formidable bacterial threats we face today. And we will ask the crucial question, is this the dawn of a new era in medicine? An era where we can finally outsmart the very pathogens that threaten to send us back to the Dark Ages? The story of modern antibiotics has been one of slow, incremental progress for the better part of half a century. The truth is, for the past 45 years, pharmaceutical innovation in this field has largely been a story of remixes, not revolutions. Scientists would take an existing antibiotic, tweak a molecule here, add a chemical group there, and hope for the best. It was like trying to win a war by simply putting new paint on old weapons. Meanwhile, the enemy, bacteria, was evolving at a breathtaking pace, developing sophisticated defenses against our entire arsenal. The result? A dwindling number of effective drugs and a growing list of untreatable infections. The U.S. Food and Drug Administration has approved only a few dozen new antibiotics in nearly 5 decades, and resistance to many of them is already frighteningly common. This is the crisis that Professor James Collins and his team at MIT's Antibiotics AI project decided to tackle, not with more tweaks, but with a complete paradigm shift. They had already made headlines by using AI to screen vast libraries of existing chemicals, discovering promising candidates like halicin, but that was like using a metal detector to find a lost key. This time, they decided to ask the AI to invent the key from scratch. They tasked their generative AI models with a monumental challenge: to dream up entirely new molecules, to explore an unimaginably vast chemical universe containing more than 36 million hypothetical compounds, and to design the perfect weapons to kill superbugs. The team employed two distinct and equally brilliant strategies. The first was like a detective story, starting with a single tiny clue. The target was one of the most stubborn and dangerous bacteria out there, drug-resistant Neisseria gonorrhea. This pathogen is a top-tier threat, becoming increasingly impervious to all known treatments. The researchers began their hunt by sifting through a colossal library of about 45 million possible chemical fragments, tiny building blocks of molecules. They unleashed a machine learning model previously trained to recognize the calling cards of antibacterial activity to analyze this massive pool. The AI acted like a master bloodhound, sniffing through the data and narrowing the list of suspects from 45 million down to a more manageable 4 million. From there, the human scientists applied their own expertise, filtering out any fragments that were toxic, unstable, or looked too much like existing antibiotics. This left them with about 1 million potential candidates. After even mere screening, they zeroed in on one particularly promising fragment, which they called F1. This fragment was their crucial clue. But a fragment isn't a weapon, it's just a piece of one. So they handed F1 over to two powerful generative AI systems to build a complete antibiotic around it. The first AI, known as CREM, or Chemically Reasonable Mutations, is like a master molecular sculptor. It takes a block of marble, our starting fragment, and intuitively knows where to chip away and where to add, transforming it into a beautiful and functional statue, a complete molecule. It makes millions of tiny, intelligent adjustments, guided by the deep principles of chemistry to ensure the final product is not only effective, but stable. The second, a sophisticated system called a fragment-based variational autoencoder, is more like a grandmaster linguist who has studied every known language of chemistry. Having read a library of over 1 million successful molecular structures, it doesn't just stick fragments together. It understands the deep grammar and syntax of how they should combine to form coherent, powerful sentences, in this case, potent antibiotics. Together, these two AI architects generated about 7 million potential new antibiotic candidates. The list was then painstakingly whittled down to 1,000, and then to a final 80 that were deemed suitable for synthesis in a real-world lab. In a testament to the challenge of turning digital designs into physical reality, chemical vendors were only able to successfully create 2 of them. One of them was a dud, but the other, which they dubbed NG1, was a miracle. In lab tests, NG1 proved to be extraordinarily effective against drug-resistant gonorrhea, and it even cured infections in a mouse model of the disease. But the truly groundbreaking part is how it works. NG1 attacks the bacteria through a novel mechanism, interfering with a critical protein called ELPTA. This protein is essential for building the bacterium's protective outer membrane, its fortress wall against the outside world. By sabotaging ELPTA, NG1 effectively rips away the bacteria's armor, causing the cell to fatally compromise itself. It's a stunning example of human ingenuity guiding artificial intelligence to solve a critical problem. If you find this fusion of biology and technology as fascinating as I do, hit that like button to let us know. But the team at MIT didn't stop there. For their second act, they decided to raise the stakes even higher. Their next target was another public enemy number 1, multi-drug-resistant Staphylococcus aureus, or MRSA, the infamous superbug that haunts hospitals worldwide. This time, they gave the AI no clues at all, no starting fragment, no preconceived notions. They simply asked the AI to generate plausible, effective antibiotic molecules from scratch, guided only by the fundamental rules of chemistry. They turned their CREM and variational autoencoder loose on a blank canvas. The AI went to work, generating an astonishing 29 million chemically plausible molecules, a universe of potential drugs born from pure computation. The same rigorous filtering process was applied. They screened for antimicrobial potential, for safety, and for novelty. Out of nearly 30 million initial designs, the list was narrowed to just 90 promising candidates. Of these, 22 were synthesized, and an incredible 6 showed potent activity against the toughest strains of MRSA in the lab. The star of the show was a compound they named DN1. In animal studies, DN1 successfully cleared MRSA skin infections in mice, proving its real-world potential. And just like its cousin, NG1, it appears to attack bacteria in a new way. DN1 also works by damaging the bacterial membrane, its primary line of defense. But unlike the precision strike of NG1, which targets a single protein, DN1's attack is broader and more disruptive, not tied to a single point of failure. And this is where the genius of DN1's design truly shines. It doesn't engage in a delicate duel with a single bacterial protein. That's an old game, a game bacteria have learned to win by simply changing the lock. Instead, DN1 wages total war on the cell's very foundation. It acts like a molecular disruptor, a sonic charge that destabilizes the entire lipid bilayer of the membrane. Think of it this way. Instead of trying to find the one key to the castle gate, it simply dissolves the castle walls. This broad-spectrum assault creates chaos and multiple points of failure simultaneously, presenting the bacteria with an evolutionary puzzle so complex that developing resistance becomes an almost insurmountable task. This isn't just about two new potential drugs. This is about a fundamental change in how we discover medicine. James Collins, the senior author of the study, said it best. Our work shows the power of AI from a drug design standpoint and enables us to exploit much larger chemical spaces that were previously inaccessible. For decades, drug discovery was like searching for treasure on a map where most of the world was marked, "Here be dragons." This technology gives us the ability to not just explore that uncharted territory, but to draw the map ourselves. The journey for NG1 and DN1 is far from over. Fair Bio, a nonprofit partner in the project, is now taking these digital prodigies and refining them through medicinal chemistry, preparing them for the long and arduous path of preclinical and clinical testing. The battle against superbugs is far from over, and these AI platforms are just getting started. To follow the next chapter in this incredible story and see what other medical breakthroughs AI will unlock, make sure you're subscribed and have those notifications turned on. The team is already setting its sights on other formidable foes from humanity's most wanted list. First, Mycobacterium tuberculosis, the ghost that has haunted humanity for millennia, a pathogen that can lie dormant in the body for years before erupting, and which has developed terrifyingly resilient strains. And then there's Pseudomonas aeruginosa, the opportunistic predator of the hospital ward, a major cause of deadly infections in burn victims, cancer patients, and individuals with cystic fibrosis. Conquering these will require even more sophisticated AI-driven strategies. But the potential doesn't stop with bacteria. This very platform, this paradigm of generative design, could be adapted to hunt for new antiviral drugs, develop novel antifungals, or even design bespoke molecules to target specific cancer cells. We are at a crossroads in human history where our own intelligence, amplified by the computational power of AI, is creating tools to solve problems that once seemed unsolvable. In a field where bacterial evolution has consistently outpaced human discovery, the ability to rapidly design, test, and validate millions of novel compounds offers a breathtaking advantage. By combining the raw computational power of generative AI with the subtle art of medicinal chemistry, we may finally have a way to stay one step ahead in the relentless race against antibiotic resistance. We are witnessing the birth of a new era, one where our greatest medical discoveries might not come from a lucky break in a lab, but from the guided imagination of an artificial intelligence. The age of AI-designed medicine is no longer a futuristic dream. It is here, and it might just be what saves us from the silent pandemic we have been losing for decades.